Hello, welcome to my YouTube channel. In this video we are going to be looking at the Poiseuille's law, which is one topic in fluid mechanics, right? So this law is a law that defines the velocity of a fluid through a pipe as a function of radius. What that means is that as you increase the radius from the center towards the edge of the pipe, right, the velocity of the fluid tends to reduce. This is due to the viscosity of the fluid. Now let's look at the diagram that describes this scenario. Now if you look at this diagram, you discover that at the center of the fluid, this is a fluid moving in this direction. This is a pipe of length of radius r from this point to this side. So you discover at the center the fluid has the highest velocity. Every particle of the fluid at the center has the highest velocity. But as you move from the center of the velocity of the tube towards the edge, you discover the velocity will reduce. This is due to the internal friction of the fluid with the surface of the tube. Okay, so in this video we want to see how we can derive the velocity as a function of the radius and other parameters. So if you look at the diagram, another diagram in this form, right, if you consider this diagram of a tube or a pipe that has a thickness where the center to the inner surface is r, while the center to the outer edge is capital letter R. If the fluid is flowing in this direction, it means that P1 is greater than P2. If the two of them are equal, there will be no flow of fluid. But if P2 is greater than P1, it means the fluid will flow in this direction. We have a length L, right? So now let's look at the force that pushes the fluid through this pipe, and it is giving us P equal to F over A. That the pressure P equal to F over A is a known fact, where our F equal to PA. So this force is what we want to study for now, and we can see that this P is as a result of the difference between these two pressure. Then our A is the cross-sectional area, the area of the cross-sectional area of this particular pipe, and that gives us F equal to P1 minus P2. This P1 minus P2 is the difference between the pressures times the cross-sectional area of this particular pipe, which is the area of this circle, and that gives us FD. Our FD, F subscript D, is the drive force, the force that drives the fluid through this direction. Then P1 minus P2, which is the difference between the pressure, times the area, the cross-sectional area of this pipe in this direction is a circle, right? The circle. So the circle is having an area of pi r squared. Okay, so if this is established, so let's look at another force that opposes this particular fluid, and which is as a result of the viscosity, and that force is called the retarding force, F subscript R, and is equal to minus mu capital letter A, which is the area of the pipe that is in contact with the fluid, then divided the R, where our R here tells us that the velocity decreases as you move towards the edge from the center of the pipe towards the edge of the pipe. Okay, so if we further establish our A is the area in contact with the fluid, and it is giving us 2 pi RL, which is a curved surface area of the cylinder, 2 pi RL, right? And this part here is the part that is in contact with the surface of part that is in contact with the surface of the fluid, right? Okay, so by the time we now check out the two forces, if the two forces are equal, the drive force and the retarding force, if they are equal, it means that fluid will move at a steady speed, or it will not move. So these are two scenarios. Either the fluid is stationary, or the fluid is moving at a constant speed. Now if we consider this other scenario where FD is less than FR, what that means is that the drive force is less than the retarding force, or we can say that the retarding force is greater than this. In that scenario, it's as if we are putting off the faucet, as we are locking the tap, so that the fluid velocity will be reducing or decelerating. But if the drive force is greater than FR, it means that you are putting on the faucet. That means it will gradually increase, but at a point this particular FD will be exactly equal to FR, which will lead to this particular. So at that point when we have constant velocity where FD is equal to FR is what we are interested in. So now that we know the expression for F drive, the drive force and the retarding force, we can equate these two together and see what comes out of it. So this is the drive force and this is the retarding force. So from here we can cancel out R, cancel out pi, and make our dV dr the subject formula. Right, so we've cancelled out our pi and we have made dV dr the subject formula at this point, where this is our L, this mu here is the viscosity of the the fluid, R is the radius of the pipe or the tube, then this V here is the velocity. So if we solve for dV using the separable variable technique, we can send dr to this point and it becomes this part here. So from here we can integrate both sides and solve for V, and from this point our dV becomes ordinary V minus V, our R here becomes R squared all over 2, and that gives us, this is a constant, leaving this one, so and that gives us our V equal to R squared over 2 plus a constant. Now it's important for us to find out what this C is. Now we notice that when R tends towards the pipe, which is as R increases to capital letter R, our V becomes 0. You know, we said the velocity of the fluid at the surface of the that is in contact with the pipe is 0 because of viscosity. So we now make this assumption that when R tends towards R, then V equal to 0. So in that case, wherever we see this R, we replace with capital letter R, then V here becomes 0. So that will now give us the value for C. So C will now be equal to minus of this expression, and that gives us this, which can be recast in this form. So since we now know that our C is everything here, that's 2 times 2 for everything here, we can substitute this C back into this expression. So we are left with our minus V equal to this part having R squared, then minus our C, which is this part, and that's what we have here, right? Okay, so on simplification we have our V equal to this, our V equal to this. If we rearrange by taking the minus to this side, we'll have this expression. So this is the velocity of the fluid moving through a pipe, right? Especially when the pipe has a thickness, right, with the inner radius R and the outer radius R squared. But if the pipe is very thin, then we can ignore this part. If it is very thin, we can ignore this part, and that leads to this part. So we can either use this or this, depending on the way the configuration of the pipe. If the pipe is very thin, just use this. If it is thick, where there is a difference between the inner circle and the outer circle, then we use this particular one. I hope that's okay. So we can now go to the next possible scenario, which is the discharge rate of the Poiseuille's law. The discharge rate of Poiseuille's law. Under this topic, we want to find out the amount of volume that comes out of the tube per second. The amount of volume that comes out of the tube per second. So to do that, we recall this formula that the V dt equal to AV and our dV dt is equal to Q. So instead of us using this one constantly, we'll just use this one. But bear in mind that our Q is dV dt and our V here is the volume, small letter v here is the velocity. So there's a connection between the volume, the amount of volume that is discharged per time, and is equal to the area times the velocity. So we can say it's equal to Q. So we can discard this one and concentrate on these two moving forward. So at this point, if we find a change in Q, a small change in Q, it must be equal to what? The velocity times change in area. Because in this case, we have seen that our velocity is constant, right? From here, our velocity is this. So it is our area that is changing. Once our area changes, the amount of volume of fluid that comes out per second will also change. Alright, so we can now substitute this into this part. Substitute this into this part, and we get dq equal to this part, then dA. Right. So from here, we know our dA is the area of the circular part of the cylinder. Right. First of all, we know that our area is what? Pi r squared. So if we differentiate our area with respect to r, it becomes 2 pi r dr. So our dA becomes 2 pi r dr, and that's what leads to 2 pi r dr. Remember that your A is pi r squared. If you differentiate pi r squared, it gives us 2 pi r dr. So we replace our dA with this part here. Then from this point, we can integrate this and see what comes out of it. So if we integrate this part, it gives us Q. If we integrate this other right hand part from 0 to R, because we're integrating with respect to R, from the center of the circle to the edge, let's see what comes out of this. But first of all, we can simplify this one further before integration, and that gives us okay, our Q becomes this part p squared all over 4 mu l, then 2 pi is a constant. Our 2 here will take care of this 4, which makes it 2. So we have this, leaving this one. Now, if we integrate this, we'll get to, remember that our r comes here. This one is a constant. It is this small letter r we are integrating with respect to. So when this r is here, it becomes r squared all over 2. When r multiplies this one, it becomes r cubed, and if you are integrating r cubed, it becomes r4 raised by 4 all over 4, and that's how we get this one. Then our limit r and 0. So in this case now, wherever we see small letter r, we'll replace with capital letter R. So in this case, we have r squared, which becomes big R raised by 4, big R raised by 4, 2 over 4. And this is what we have. So from here, if we simplify this one, it's like saying half minus 1 over 4. That will give us what? 1 over 4. Right? And that gives us this expression. So if we simplify this one, it gives us this. So this formula is the discharge rate of fluid through a cylindrical pipe. Right? So let's quickly look at one of the implications of this formula. It's very, very important to know the implication of this formula. So the implication of the Poiseuille's law. So if you consider this formula, right, you can tell that if the radius is reduced by half of the pipe, if the radius of the pipe is reduced by half, let's see how it affects the discharge rate. So in that case, our R all over 2 all raised by 4, right, equal to a new discharge rate, which is Q1. So if we simplify this one, it gives us 1 over 16, because this 1 over 2 raised by 4 is 1 over 16. It comes out, then leaving this part. And we now know that everything here is TQ. So in that case, we now have our new Q1, which is equal to the old Q divided by 16. So the implication of this formula is that once you reduce the radius of the pipe by half, it in turn reduces the discharge rate by 1 over 16, which is very huge. What that means actually in human body is that when we have so much fat in our blood veins, which reduces the radius or the size of the inner wall of the veins, you realize that the amount of blood that is supposed to be pumped to a particular region will be reduced by 1 over 16, and which will require that the heart will do more work in pumping more blood to that particular region. So it's very important that we should take notes, and this kind of problem is seen among those who are obese, right? That's why you see the heart palpitates regularly with high speed. So that's the implication, and I hope you learned one or two things today. Thank you for watching. Please like, share and subscribe to this YouTube channel so that I can get the latest content from this channel. Thank you.